Hi everyone, I'm Danny from Huawei Mass Data Storage Domain. Today I'm going to talk about the performance challenges facing HPC and how Huawei will tackle these challenges. Nowadays, an increasing number of HPC applications are being used, and these vary in I/O models. For example, there is the large I/O bandwidth intensive model, the small I/O IOPS intensive model, and the metadata OPS intensive model. There is also a parallel I/O model in which applications adopting the MPI framework concurrently access the same file. The convergence of traditional HPC, big data, and AI means that heterogeneous computing such as ARM, GPU, and FPGA requires increasingly higher storage performance. The greatest challenge facing HPC is how a storage cluster delivers high bandwidth, high OPS, and ultra-low latency for a hybrid workload model. Before we answer this question, we need to understand the typical scenarios involved in hybrid workloads. The first is the supercomputing center. In this scenario, services are typically provided in leasing mode. Different tenants run different applications and test cases, such as those for weather forecasting, genome sequencing, and wind resistance simulation. The applications have varying I/O workload characteristics, but tenants typically share one storage system to serve all these applications. Second, in emerging AI scenarios, the bandwidth, IOPS, and latency requirements in pre-processing, training, and simulation phases all vary. Last, in typical enterprise scenarios, such as the oil and gas exploration industry, different storage products are configured for seismic data processing and interpretation because they differ in I/O models. However, if we use just one storage system, we can avoid data copying between storage products, greatly improving application efficiency and reducing storage construction costs. So, why is performance a challenge in storage systems in hybrid workload scenarios? The difficulty is that the bandwidth and IOPS intensive scenarios have different performance measurement standards, software stack scheduling policies, and optimal media access models. In some cases, there are even requirement conflicts. First, in bandwidth intensive scenarios, performance is measured by the data throughput in a unit time. In such scenarios, the number of I/Os in a unit time is small, but each I/O is large and the processing of each I/O is time consuming. By contrast, in IOPS intensive scenarios, performance is measured by the number of I/O requests processed in a unit time and the latency in processing an I/O request. In such scenarios, a large number of I/O requests are frequently initiated in a unit time, and each I/O request must be handled within a very short time. Hybrid workloads can cause conflicts in CPU scheduling policies and request queue management. Bandwidth-intensive workloads need minimized CPU switchovers, but IOPS-intensive workloads require CPUs to be switched over between requests as soon as possible to ensure a low latency in processing each request. If IOPS-intensive requests queue after bandwidth-intensive requests, the latency of IOPS-intensive requests cannot be guaranteed. Second, in bandwidth-intensive scenarios, the network, disk, and memory bandwidths are the main performance bottlenecks. To mitigate these bottlenecks, we need to reduce the network forwarding, memory access, and data redundancy while ensuring data reliability. In IOPS-intensive scenarios, the CPU computing power and the software call stack depth are the main bottlenecks. To mitigate these bottlenecks, we need to reduce request amplification and software call stack depth. So, for hybrid workloads, the challenge is how the logic for processing a software call stack achieves both the minimum bandwidth application and the thinnest software stack. Last, let's have a look at the media access model. For bandwidth-intensive workloads, a larger I/O size and less metadata result in higher continuity of disk LBAs, meaning higher performance. For IOPS-intensive workloads, a higher match between I/O size and disk management granularity, as well as smaller I/O amplification, result in higher performance. So, under hybrid workloads, the major challenge lies in how data layout balances between the processing of large and small I/Os. To address these challenges we just mentioned, we launched the next generation OceanStor file system named OceanFS. With multi-dimensional innovations, Ocean FS solves the problem caused by the coexistence of bandwidth and IOPS intensive workloads. We use a series of key technologies to deliver superior bandwidth performance. For example, Smart Cache implements large I/O pass-through to reduce network amplification. High ratio EC reduces disk bandwidth amplification. Copying and verification integrate to reduce memory bandwidth amplification. And the append-only disk layout technique enables sequential disk I/O access. In addition to high performance, Ocean FS delivers high IOPS and low latency. For example, we aggregate small I/Os in Smart Cache, eliminate distributed locking, and adopt one-way RDMA for Smart Cache to fully release the CPU computing power and decrease the software stack depth. Key technologies such as intelligent CPU scheduling, end-to-end QoS mechanism, and multi-granularity disk management resolve the conflicts between bandwidth and IOPS intensive workloads. Let's have a quick look at some of these key technologies. First, let's review the Smart Cache feature. We know that in the process of writing data to a traditional storage array, all I/Os are first delivered to the memory. After a copy is mirrored between controllers, the storage array will then return a response. This practice ensures the shortest path and the lowest latency for small I/Os. However, there are two key issues. The first is that copy mirror doubles network and memory bandwidth amplification. As a result, only half the network and memory bandwidths can be provided for workloads at most. The other issue is that copy mirroring doubles the workload volume processed by CPUs, making the CPU bottleneck more serious in small I/O scenarios. To deal with bandwidth amplification, the Smart Cache feature of Huawei Ocean FS directly transfers large I/Os from clients to disks, reducing network and memory bandwidth amplification. And small I/Os are aggregated through one-way RDMA mirroring, which reduces the CPU overhead by 30% without increasing the software stack depth. This ensures a low latency and improves IOPS performance. Next, let's talk about how we eliminate the use of distributed locking. To achieve load balancing and capacity balancing, a distributed storage system typically implements at least two distribution logics. One is the metadata service distribution logic, and the other is the object storage distribution logic. The two distribution logics balance the metadata access loads and the use of storage capacity. When concurrently accessing a directory or file, multiple nodes may operate the same metadata or data object at the same time. So distributed locking is needed to ensure the data consistency in parallel access scenarios. However, distributed lock operations may cause huge system overheads. To eliminate the use of distributed locking, Ocean FS innovatively implements one-time distribution based on directory partitions, introduces the ownership-based forwarding mechanism that is often used by a centralized architecture, and integrates the metadata, distributed locking, and data access services into one role. Only one message interaction is required for small I/Os, greatly reducing the CPU overhead and request latency. Next, let's go over intelligent software stack scheduling. To achieve optimal performance under hybrid workloads, Ocean FS uses an intelligent CPU grouping algorithm and end-to-end QoS to implement software stack scheduling policies that are adapted to I/O sizes. First, based on the characteristics of large and small I/Os, the dynamic CPU grouping technique automatically separates large and small I/Os into two queues and specifies CPUs for the queues, so that some CPU cores are dedicated to handling large I/Os and some to small I/Os. This ensures a high bandwidth is provided for large I/Os and a low latency is maintained for small I/Os. Second, to achieve an ultra-high bandwidth and ultra-low latency, each I/O is always processed by one CPU core. A context switchover is not needed during the intermediate processing, reducing all unnecessary system overheads. Last, the system automatically identifies I/O priorities for foreground and background applications, metadata and data operations, as well as request and response messages. The end-to-end QoS mechanism ensures that foreground applications take precedence over background applications, metadata operations over data operations, and response messages over request messages, achieving an ultra-low latency in hybrid workload scenarios. Next, let's turn to data management. Mainstream file systems usually use the write-in-place approach for disk management. After a file system runs for a long time, however, repeated file creation and deletion result in severe data fragmentation on disks. As a result, each of the subsequent large I/Os is split into multiple small I/Os, and a longer runtime results in more severe fragmentation and lower bandwidth performance. In contrast, OceanFS innovatively introduces the append-only data management approach. New data is always appended to consecutive empty locations. Garbage collection is performed for invalid data in the background to release consecutive disk space, ensuring continuity of large I/Os on disks. This mechanism delivers high bandwidth and IOPS performance for hybrid workloads. Finally, let's talk about the multi-granularity disk management technique. As I mentioned before, greater continuity of large I/Os results in a higher disk bandwidth. However, if only large granularity indexes are used, small write I/Os will be amplified several times, affecting the performance and latency in handling small I/Os. On the other hand, if only small granularity indexes are used, a large amount of index data will be generated, leading to a huge metadata overhead. This affects the bandwidth for reading and writing large files. To resolve this conflict, OceanFS uses the multi-granularity disk management technique and implements two-level indexing. Parent indexes have a fixed length and large granularity, delivering a high bandwidth for reading and writing large I/Os. Child indexes have a variable length and small granularity, which can automatically adapt to I/O sizes for flexible read and write of small I/Os to prevent I/O amplification in small I/O scenarios. In addition, OceanFS automatically optimizes the data index structure through defragmentation. Such a design ensures high performance under hybrid workloads and lays a solid foundation for implementing variable length deduplication and compression. That's all from me today. Thank you for joining me, and see you next time.